Hello students, welcome back. Today we will discuss about electric potential due to dipole. Electric dipole is a system of two equal and opposite charges separated by a certain distance. Let this is the center of dipole. Positive and negative charge, let's say each of magnitude q. One is positive, another is negative. They are separated by distance twice a. Each charge that is at equal distance a from this center. Here a dipole moment, the direction of dipole moment, it is from negative to positive charge. So direction of dipole moment P, that is from negative to positive charge. If you want to find electric potential at any point, let's say at any point P, let the distance of point P from the center of dipole, if it is R, then what is the electric potential due to this dipole at point P? As we know, electric potential due to point charge equation, it is kq by R. Here we have both the charges. What we need are the distance of each charge from point P. Let the distance of positive charge from point P, let's say it is R1, and the distance of negative charge from point P, if it is R2, then we can say that the potential due to positive charge at point P is kq by R1, and potential due to negative charge is minus kq by R2. Also, potential, as it is a scalar quantity, that's why total potential or the net potential at point P we can write as V due to positive charge plus V due to negative charge, and that is why kq by R1 minus kq by R2. So here you can write kq common 1 by R1 minus 1 by R2. If we find the value of this R1 and R2 in terms of R, then this equation can be written in another form also, as let us find the value of R1 and R2 in terms of R. So here R vector, it is making certain angle theta with the direction of dipole moment P. If distance R is much larger compared to the length of dipole, then taking the projection of this vector R1 on this vector R, you can find this value. This will be, by drawing this perpendicular here, you can write this value as A, opposite side, so it is a sin theta, and this value will be A cos theta. So you can write value of R1 as R minus A cos theta. R1 will be equal to R minus A cos theta. If you take R common from this, you can write 1 minus A by R cos theta. Here you need 1 by R1, so you write here 1 by R1, that is equal to 1 by R. This comes into denominator, you can write 1 by R cos theta raised to minus 1. A by R. A is very small compared to R, so A by R is less than 1. Cosine function maximum value it can be 1, so A by R cos theta factor is less than 1. So if you do the binomial expansion of this, you can write as this is equal to 1 by R, 1 plus A by R cos theta. So this is the value of 1 by R1. Similarly, expanding this, if you draw perpendicular from minus q on this R, then this value will be again A cos theta, and the value of R2 will be equal to R plus A cos theta. But 1 by R2, if you find, that will be 1 by R into 1 minus A by R cos theta. This values, if you put in this equation, you can write kq 1 by R1, that is 1 by R cos into 1 plus A by R cos theta, minus this is 1 by R into 1 minus A by R cos theta. So V at point P is equal to, you can write K 1 by R is common, so it is KQ by R. What is left inside now? 1 plus A by R cos theta minus 1 minus plus A by R cos theta plus 1 minus 1 cancel. So what is left? That is KQ into A by R cos theta plus A by R cos theta to A by R cos theta. This R becomes R square cos theta. Now Q into twice is dipole moment P, that is why 2P Kp cos theta by R square. This is the equation for potential at any point P due to dipole. Here if value of theta is 90 degree, if theta is 90 degree, that is equatorial point, then value of potential will be 0. If theta is 0 degree, cos 0 value is 1, V at point A will be equal to Kp by R square. If theta is 180 degree, cos 180 is minus 1, so potential at point P is equal to minus Kp by R square. So this way, at a different points, at any point you can find the potential due to dipole taking value of theta. Okay. So this is the expression we are finding potential due to dipole. Another is electric potential energy. Electric potential energy for system of charges is defined as the amount of work done in bringing a charge from infinity to any point in electric field due to another charge. Let us consider charge Q1 is there, around the charge Q1 there is electric field. If we bring charge Q2 from infinity to point P, the amount of work done in doing this process is stored as electric potential energy for system of these two charges. So to find this work done, we have to divide this whole path into small elements. Let's say each of length dx. Let the element is at a distance x from charge Q1. Charge Q2 is brought from infinity to this point. The work done for the small displacement we can write as dw is equal to f dot dx. Here force acting on charge Q2 due to Q1 when at a distance x is k Q1 Q2 by x square into this force. If both have like charges, the force is repulsive. We have to bring it along this direction. Displacement is dx. Angle between them is, as we write, f dx cos theta. Theta is 180 degree, cos 180 is minus 1, and that's why we can write this minus sign as here, and that's why this equation of work done dw for small displacement dx. If you want to find out the total work done, you can find the total work done is the integration of this dw, range of integration from infinity to up to point P. And that's why you can write total work done is equal to, in moving charge from infinity to point P, W infinity to P, you can write like this, W infinity to P, that is, here K is constant, Q not constant, negative sign is also taken out, integration of 1 upon x square dx, limit from infinity to point P is at a distance r. So if you put the value of this integration, it is minus 1 upon x, limit from infinity to r. Negative sign will cancel. What is left? That is k q not, putting the value of limit 1 by r minus 1 by infinity. 1 by infinity is 0, so it is k q not by, this is the work done in moving charge from infinity to point P, and this work done will be stored as a potential energy for the system of these two charges. That's why we can write potential energy of the system of these two charges is k q not by r. So this way you can calculate the potential energy for system of charges. Here there are two charges, so for the system of two charges this is the equation. Now as you know, potential is the amount of work done in bringing unit charge from infinity to any point in electric field, whereas potential energy is the amount of work done in bringing charge from infinity to any point in electric field. So there can be a relation between electric potential and electric potential energy. As you know, potential energy for a system of two charges Q1 Q2 separated by distance r is U is equal to KQ1 Q2 by R, whereas potential due to charge Q1 at distance R is KQ1 by R. If we bring charge Q2 from infinity to at a distance R from charge Q1, then work done we write as potential energy U is KQ1 Q2 by R. And KQ1 by R is what? Potential due to charge 1. That's why we can write U is equal to V into Q2. So this is the relation between potential energy and potential. Okay. Potential energy of system of three charges. Let's consider three charges Q1, Q2 and Q3 initially at infinity from each other. If you bring charge Q1 from infinity to this point, as in this region there is no electric field, work done in bringing this charge 1, it is 0 because it is brought in absence of external electric field. There is no electric potential in this region, so work done is 0. Now in presence of this charge Q1, if I bring charge Q2 from infinity to, let's say, up to this point, which is at a distance R12, then at this point potential due to charge Q1 is, if I write as V1 at this point, that is KQ1 by R12. And because of that, work done in bringing charge Q2 at this point is V1 into Q2, that is KQ1 Q2 by R12. So this way, work done in bringing charge Q2 in presence of charge Q1 is this. Now in presence of these two charges, if I bring charge Q3, let's say charge Q3 is brought here from infinity, then the distance, if it is, let's say, R13, this distance, let's say it is R23, then at this point potential due to charge 1, it is KQ1 by R13, potential due to charge 2, it is KQ2 by R23. So net potential, that is sum of these two, and that's why work done in bringing charge Q3, it is V1 plus V2 into Q3. And V1 here it is KQ1 by R13 plus V2 is KQ2 by R23 into Q3. So total work done here it is KQ1 Q3 upon R13 plus KQ2 Q3 upon R23. These are W3. So we can say net work done, or total work done for the system of these three charges to assemble it, total work done, W is W1 plus W2 plus W3. If you put the values, W1 is 0, W2 is K, Q1 Q2 by R12, K Q2 Q3 by R23 plus K Q1 Q3 by R13. So this is, we can say, potential energy for a system of these three charges. So this way, whatever number of charges are there, you can find the potential energy of the system. Next is potential energy of a system of charges in presence of external electric field. Let's say in this region the external electric field is there, and because of that at different point there is a different electric potential is there. In presence of this external field, if we bring any charge, let's say Q1 from infinity to up to this point, then as it is brought in presence of the external field, at this field point external field potential is V01, and that's why the work done in bringing this charge Q1 is, it is V01 into Q1. This is the work done. Now in presence of this charge Q1 as well as the external potential V02, if we bring charge Q2 at this point, then at this point there are potential, one that is due to external field, another due to charge Q1. That this distance is R.2. Then at this point now net potential will be V02 plus potential due to charge 1, that is KQ1 by R12. In presence of this charge Q2 is brought. So work done is this. Now in presence of these two charges, if I bring charge Q3 here, where distance of charge 1, if it is R13, distance of charge 2, it is R23, then in that case work done will be W3 will be equal to 1, that is potential here due to external field, that is V03, plus potential due to charge 1 is KQ1 by R13, plus potential due to charge 2 is KQ2 by R23. In presence of this, if I bring charge Q3, the total work done of this system to assemble this is, now we can say W is equal to V01 into Q1 plus V02 into Q2 plus V03 into Q3 plus KQ1 Q2 by R12 plus KQ1 Q3 by R13 plus KQ2 Q3 by R23. So we can say the potential energy of the system here, 3 more terms it is added compared to the absence of external field. So net potential energy is V01 Q1, V02 Q2, V03 Q3 plus KQ1 Q2 R12, KQ1 Q3 R13, KQ2 Q3 R23. This way, potential energy of the system you can find in presence of external electric field. Next is electric potential energy of a dipole placed in uniform electric field. Let us consider in this region there is a uniform electric field which is represented by parallel field lines with equal spacing. In this, let the electric dipole is placed having positive charge, negative charge. Force acting on this is plus QE, force acting on this is minus QE, means acting in the opposite direction of electric field. Dipole moment, it is from negative to positive charge. Electric field, this is the direction, this angle is theta, angle between electric field and dipole moment. Now, when this dipole is placed into electric field, due to the torque acting on the dipole, it will rotate in the direction of applied field. Dipole moment will align in the direction of applied field. The torque acting on dipole is tau is equal to P cross E, that is equal to PE sin theta. As you know, torque is also defined as rate of doing work, dW by d theta. Torque is the work done per degree twisting. So, equating these two equations of torque, you can write dW is equal to PE sin theta to d theta. dW by d theta is equal to PE sin theta, dW is PE sin theta into d theta. It means that dW is the amount of work done in rotating the dipole by angle d theta. If you want to rotate it by certain angle theta, what is the total work done? Work done in rotating dipole from angle theta 1 to theta 2 is W is equal to integration of PE sin theta d theta, limit from theta 1 to theta 2. This P and E are constant here. Integration of sin theta, it is sin theta integration is minus cos theta. So you can write minus cos theta, limit from theta 1 to theta 2. So you can write PE cos theta 1 minus cos theta 2. Negative sign is taken inside. So you can write the equation of potential energy is PE cos theta 1 minus cos theta 2. So this way, using this equation, you can find the potential energy of dipole. Now, if you take different values, if theta 1 is equal to, initially let's say theta 1 is 0, cos 0 value is 1. If theta 2 is 90 degree, cos 90 is 0, then in that case potential energy will be PE into 1 minus 0 is equal to PE. If theta 2 is 180 degree, cos 180 is minus 1, therefore U will be equal to PE into 1 minus minus 1, that is equal to twice PE. So this is the maximum potential energy. If theta 2 is 0, cos 0 is 1, in that case U is equal to PE into 1 minus 1, that is 0, is the minimum potential energy. So you can say theta, that is angle between direction of electric field and dipole moment, when theta is 0, means dipole is aligned in the direction of electric field, it is having minimum potential energy, whereas when it is anti-parallel, it has a maximum potential energy. Remember, in both these cases, torque acting on the dipole is 0. So we can say that theta is equal to 0, it is stable equilibrium, whereas theta is equal to 180 degrees, unstable equilibrium, because at theta is 180 degree, potential energy is maximum. So you can write here, this is condition of stable equilibrium, and theta is 180 degree, this is unstable equilibrium.